Physical science time. Let's talk about machines. Let's talk about machines quickly if we can, huh? Okay, so machine we have defined as you wrote in your vocabulary. A machine is something that we use, a device that we use to make work easier, right? And we're talking about here the scientific definition of work, not the layman's definition where work is just something that we do to make money. So the scientific definition of work, remind me, is what? As an equation, please.
The scientific equation for work?
Yeah. Go ahead, Alyssa.
Work is force cross distance.
Yeah. Work equals force cross distance, right? Work equals force cross distance. And what units do we use to measure each of these things? Work is measured in joules. Force is measured in newtons, and distance is measured in meters. So how can we make, remember, when we're doing work scientifically, we're applying a force to move an object a distance. So there are several ways that we can make this easier. Easier by doing what? Just let's think of some ideas. How can we make this process easier? So remember, because of the, well, I was going to have, how about you name it? We know that this, if we negate friction, right, if there's no friction at all, this will be the same before and after y, because of the law of conservation of energy. So can we make it easier by making there be more energy afterward?
No.
No, of course not. So we can't, that's not a choice.
Force
Okay, yeah, so we could lower the force.
and higher the distance.
Well, yeah, we could, I mean, that, is it always advantageous to make the distance shorter?
No.
Sometimes it would make the work easier to lower the distance, right?
All the time.
A lot of the time. And there's another way that we don't always think about, but just because of, we're biological organisms, and some of our muscles are easier to run than others. What is another way that we could change this? It's not really, it is in the equation, but it's not really like expressly stated in the equation. What else can we do with a machine? So some of them lowered the force. We talked about the types of simple machines. Some of them decreased the distance. What was another thing that many of the simple machines did?
Makes it easier.
Yeah, but how?
Yeah.
By doing what? Yeah, changing the direction. Changing direction of applied force, right? And so, is that expressed, okay, so it's not expressly mentioned in this equation, but this quantity and this quantity both have distance. Remember that we had to have them act in the same distance in order to be able to calculate work with a simple mathematical equation. There are ways to calculate this if they're not in the same direction, but for us to do it just by multiplication, we had to have them in the same direction. So direction is a component of this. Can you give me an example of something that would be easier, even if we didn't change either the force or the distance, but we just changed the direction? A screw, yeah, because we're trying to fasten, usually when we use a screw, we're trying to fasten, for instance, two boards together, and it's easy for us to apply rotational force because we don't have to actually move it up or down, right? So we use, as you probably are aware, we use a screwdriver and a screw in the same way that we use a hammer and nail, right? They have the same job, but with the hammer we're applying a downward force when we're putting it in, we're applying an upward force when we're taking it out, but it's generally easier to just use the twisting force of the screw because it kind of puts itself in, basically. And same thing when we undo it, it takes itself out. So a lot of times the simple machines don't really do anything other than just change the direction. Another example I was thinking of is you might have some blinds at your house that have like a pulley on them, right? And when you pull down, the blinds do what? They open up, right? So is it possible to make blinds that you just lift up? Well,
Yeah.
sure it is. Of course it's like. In fact, the blinds over there, these are the rolly type blinds. If I could show you on camera, I would. But basically the little apparatus in there, it's more than just a simple machine, but it makes a downward force when you pull it down into an upward force. Anyway, so there are several ways the machines make the work easier. And we have a little formula that we sometimes use with this, and it's called mechanical advantage. Mechanical advantage. Sometimes, when we're talking about it in a frictionless a frictionless environment, we sometimes call it ideal mechanical advantage if there's no friction. If we negate friction, because in truth, I spelled it wrong. In truth, there is friction. What's friction do to this equation all the time?
Hangs it.
Well, so does it actually change the amount of energy before and after?
No.
No, but it does change the amount of useful energy, right? Because it changes all kinds of energy, specifically kinetic, but any kind of mechanical energy into what? Into friction turns kinetic energy into thermal energy, right? Have you ever pounded a nail? Raise your hand if you pounded a nail into something. Let me change the question. Have you ever taken a nail out of something? Have you ever pried a nail out of something? Keep your hand up if you have. Have you ever felt the nail afterward?
It's a little warm.
It is hot, right? And it's because of friction. It's because of friction. However, if we negate friction, would a nail work at all? No, the nail works just on friction, right? If there was no friction, you could just pluck the nail out, which would be bad. Anyway, so that we call it, but we do, in order for our calculations, we call it the ideal mechanical advantage if we negate friction. So sometimes we abbreviate mechanical advantages as MA and ideal mechanical advantages as IMA.
Oh, so that's what the assignment
Look.
on the assignment.
Yep, exactly. Look with me at the equation for mechanical advantage. It says mechanical advantage equals output force divided by input force. So mechanical advantage, MA, equals F out divided by F in. Right? The output force divided by the input force. This is a very simple equation because what unit do we measure this in? So what unit do we use to measure both of these? Okay, and then just with simple algebra, what would happen if we do this operation? What's the unit going to be?
Percent. Oh, okay.
What's this? Solve this algebra problem. 1. So what's the unit going to be if we divide newtons by newtons?
1. So 1.
1's not a unit. It's just gone. There's no unit. MA is unit less. Please write that down. If you're measuring mechanical advantage, it should be unitless. It's going to show up as a fraction, or it could be greater than 1, but it's going to be some number between 0 and 2. 1 would be, if the mechanical advantage is 1, it means whatever force you put in, that same force comes out. And that's not always a problem, right? It's not always the way we want it, but it's not always a problem. For instance, if we're just changing the direction, the force that we apply, what was our example for the changing direction one? The screw, yeah. The same force we applied as a torque, but the same torque that we apply to the screw forces the screw in, right? We're not changing the force at all. It's just changing the direction. Same thing with the blinds, right? We're applying the same force as if we lifted the blinds up. It's just easier as a human being to pull things down than to lift them up generally. The other thing we need to talk about is efficiency. And you've heard the word efficiency before. This is another word. In fact, this whole chapter is riddled with words that we use in daily usage that we also have scientific meaning for. But in science specifically, efficiency is a measure of the work that we get out of something compared to the work in. So here, efficiency equals work out divided by work in. Oops. Work in. Bad erase. Work in. And this we measure in percentages, so we multiply it by 100%. So once again, joules divided by joule is still unitless, but here, percent almost acts as a unit, right? Because we multiply it by 100%. This is the same thing you do when you get your grade back on a test and it says 65 out of 70, and then I have the percentage written next to it. It's just the same as if you divided 65 by 70 and then multiplied it by 100%. This is a very common mathematical operation to get percentages. So, what makes the workout change? Why would these ever be different? We just said that this is always going to be the same as the workout. What is the number one thing? The only thing, really. There's a few. What is it? Friction. Friction. There's a couple. There's other things. We talked about it before. What other energy transfers always occur when we're doing something like this? Friction is generated, right? It turns into thermal energy. What else? Remember? Sound and deformation was the third one. So, nope. Friction, sound, and deformation. So because of those, which one of these will always be less? Work out will always be less. So this efficiency is always In fact, we could in this universe we could write efficiency is always less than 100%, but technically, because of the way the equation is, it could be less than or equal to. Because of the three things I mentioned in our universe, in the actual way that things are, it's always going to be less than 100%. But you could imagine an equation or a universe where it would be exactly 100%. But it can never be more because of, once again, the law of conservation of mass. Different, let's turn with me please to page 141. In general, the mechanical advantage equation, that's it for efficiency. In general, the mechanical advantage equation is force out divided by force. And look on page 141. This is, you don't have to have these equations memorized. We're just going to talk about them a little bit. Right here it tells you the ideal mechanical advantage for a lever. You see that? How do we calculate the ideal mechanical advantage for a lever? The length of the input arm divided by the length of the output arm. This one is force out divided by force in. That one is length in divided by length out. Why would it be switched from these? Well, in the same way that we talked about like force cross distance, if work stays the same and force gets bigger, what must happen to the distance? The distance gets smaller, and the reverse is true too. If the force gets smaller, the distance must get bigger. And so, for the ideal mechanical advantage of a lever, it's length in divided by length out. Okay? Look with me now at the ideal mechanical advantage on the next page on 143 for a wheel and axle. It says radius of wheel divided by radius of axle. First of all, for measuring radiance, which of these things is radius? The distance. And so, judging by what we just learned, if our length has to be length in divided by length out for ideal mechanical advantage, what are we considering the input of our wheel and axle? The top one, which is the radius of the wheel. That counts as the input force, the input length. And then let's look now at the one for the inclined plane, which is the ideal mechanical advantage of an inclined plane. It says length of slope over height of slope. An inclined plane, which one of these are we trying to increase? We're trying to increase distance by using an inclined plane, right? The classic example is, here's the moving truck, right? Instead of having to lift the big old burden up and into the truck, we instead use an inclined plane where we end up pushing it further, but we don't have to apply the big amount of force, right? So by doing that, we make the force smaller and the distance larger. Because we can't ever do more work, right? The conservation of energy says no. But we can change the ratio of force to distance effectively. That's why we use simple machines. To either lower the force, lower the distance, or change the direction of the applied force. Questions?